So, all right, let's begin. Do you mind shutting your laptop back there? Yeah. This is the home stretch, the final lap, and those in the classroom are the only ones actually finishing the race. That's kind of good for you. We are into our last 4 lectures. The last 2 lectures that I will be giving the next week are supposed to be guest lectures, but I might just change my mind. So don't count on it. In the next couple of lectures, we're going to talk about a very special kind of network. So the stuff we've seen so far had to do with networks of the kind that we have in the upper picture, where you had information or data coming in at one end, it went through the network, and the results came out the other end. What we haven't looked at are networks like these, where the output of one neuron eventually feeds back into the neuron itself, loopy networks. Everything has been feed forward. How do loopy networks behave? So let's say we're going to consider this very simple network, but you can generalize this idea, where we have a collection of neurons. The output of every neuron goes to every other neuron. And we'll consider a very simple activation function, the threshold activation, which outputs a 1 if the input is non-negative and a -1 otherwise. So we're using a 1 - 1 labeling because it makes explanations somewhat simpler. And to simplify matters more, I'm going to assume that the weights are symmetric, which means the weight of the connection from this neuron to this one is the same as the weight of the connection from here to here. So I don't have to draw 2 different arrows like I have over here. A single arrow does the job. And again, the activation is a threshold activation. Now how do you think such a network would behave? Does anyone want to guess? What would happen? Anybody? Bishop.
The values would blow up because they would feed into each other.
They can't blow up, right? Because the output is either 1 or -1. So what would happen? So let's see, right? Now this is what is called a Hopfield network. This is a loopy network where the weights are symmetric, but everything that we discuss over here can be generalized with if you feel like it. Now, so here's what we have. Each neuron, so let's consider that all of the neurons have some current output, which is either +1 or -1. Now, each neuron is going to receive an affine value of all the other neurons. So it's a weighted sum of the outputs of all the other neurons plus a bias. This is what I'm going to call the field at the neuron. And the neuron is going to output a +1 if this value is positive and -1 if this value is negative. Now let's think about it differently. If the neuron is currently a +1 and if the field is +1, is the neuron going to change its output? Yes or no? Right? And if the neuron is a -1 and the field, the affine value at the neuron is also negative, is the neuron going to change its output? Also nil, right? So what is the condition under which the neuron will change its output? When the field and the neuron output are opposite signs, right? And so at each time, the neuron receives a field, and if the sign of the field matches the sign of the output, the neuron doesn't change, otherwise it flips itself. Y becomes -y if y times the field is negative, which means that the current output and the field have opposite signs, right? And so a neuron flips if the weighted sum of other neurons' outputs is of the opposite sign to its own current output value. But this may cause, or rather the affine function has a different sign from the current output value. But then, if that happens, once the neuron flips, the field at the other neurons changes. Those neurons might flip now, right? But when those neurons flip, their field has changed. Their contribution to the field over here has changed. And now the field at the current neuron may change. And the neuron may flip right back, right? And so you're going to have behavior of this kind. If the field if they consider, say, this neuron, the field here doesn't match its current output, so it's going to flip. But because it's flipped, the field out here has changed, so that's going to flip. And this can cause the original neuron to go back and flip again. So here is a simple loopy network of this kind, where I've set the network at some value, and I just let it evolve 20 times, 20 steps, and you can see how all of the neurons keep flipping, right? Now this is kind of too brief, only 20 evolutions. Here there are 120, you can see exactly what's happening over here, right? And the neuron can flip multiple times, because when it flips, it causes other neurons to flip, which may change its own field, and then this neuron is also going to flip, right? How long will this behavior continue? Anyone? Will it continue forever? Pardon me? It could continue forever. How many of you think it would continue forever? Right. And how many think it couldn't? And some of you don't have an opinion. You're just looking at me, right? So why do you have no opinion? If they all become the same sign, then the field at some, we didn't say the weights are all positive, right? So then it would cause some things to flip. So there is in fact a fixed upper bound on, there are conditions where it can keep flipping. It's ringing after all, right? This is like ringing. But in terms of, but you can show that the final configuration that it's going to arrive at is going to be arrived at in a finite number of steps. Why so? So look at it this way. Let's consider any neuron. Y minus is the output of the neuron before it has considered the current field, right? And Y plus is the output of the neuron if after it responds to the current field. Now, Y minus times this, Y plus will be different from Y minus under one condition. What is that? Come on, guys. Yes.
It's connected with a neuron that's the opposite sign.
Not a single neuron, but if the field at the neuron, the weighted sum is of the opposite sign, correct? And so what will happen is if Y minus is the same as the sign of the field, then Y plus equals Y minus, correct? But if they're opposite signs, then Y plus equals minus of Y minus. Yeah? So Y plus times the field minus Y minus times the field is going to be 0 if the current output of the neuron has the same sign as the field, because the neuron has not flipped. On the other hand, if the sign over here of the field and that of the neuron are not the same, it's going to flip. And once it's flipped, it flips, both of them are going to have the same sign, right? Which means Y plus times the field is always going to be positive, right? Y minus times the field, if the field and the current output match, it's also going to be positive, the difference is 0. If the product is negative, then because the neuron output flipped, this guy is minus of Y plus, right? It flipped. And so the result is going to be 2 times Y plus times the field, right? Eric, question?
I don't follow. That's fine.
Okay. So where did I lose you?
Why that conclusion means that it must converge.
Why?
All the math makes sense.
Yes, why this means it must converge. Okay, let's get to that, right? So what we are saying is that each flip of a neuron is guaranteed to either not change this value or increase this value. Everybody with me so far? Questions? Right, okay. So this is easy. So let's sum this value over all of the neurons. This guy here is the product of the field and the value of the neuron at any given neuron. Let me sum this over all of the neurons, right? I'm going to call this my term D. So this is just, if you actually look over all of the neurons, this is the product over all pairs of neurons of the weight connecting the two neurons times the value of both neurons. This is just regular math, right? And the second term is plus BIYI is just the additional bias term. So is this equation making sense so far? Right? Nothing complicated, right? Now, anytime a neuron flips, so let's say the kth neuron, right? So this difference, this value, this D with YK after the flip minus d with yk before the flip is simply going to be 2 times yk plus times the field at the kth neuron. This is basically what we said right earlier. If a neuron flips, then this d value changes by 2 times y times the field. Again, I haven't written anything particularly complicated here. Does it make sense? Right? So what is the smallest value for this? Here's what
0?
we have. 0 if it doesn't flip. If it flips, well, so here's what we have. This is what we had for D, right? So what is the upper bound on D? The upper bound on D is simply going to be, because the y's are all either +1 or -1, right? So the upper bound on D, this is just going to be the sum of the magnitudes of the weights times the sum of the magnitudes of the biases. This is the upper bound on D, correct? The lower bound on this difference is simply going to be y is either +1 or -1. So 2 times this guy over here, the smallest of these. So you consider the field at every neuron, and you take the smallest field, and twice the magnitude of that smallest field is the smallest that delta D can be. Correct? And so how many steps? Each step is going to, anytime there's a flip, you're going to have at least this much change. The maximum value of D is this guy. So if each flip has a lower bound and the maximum value that the objective can take is bounded, then the maximum divided by the smallest change is going to be the maximum number of steps before the objective hits the max. Right? Alright, that makes sense?
I feel like you could pick weights and biases that would make the top term negative.
I'm taking the magnitude.
Why the magnitude?
Because if you give me, that's upper bound, right? If you make them negative, it's going to be smaller. If I take, this is the absolute upper bound. If the weights are negative, if some of those terms are negative, then the maximum value of D is actually going to be smaller than that. Right? So I'm taking the upper bound. So this means that any sequence of flips, because D max has a finite value and D min has a lower bound, D max over delta D min is going to be the maximum number of steps after which there's no more change, because any step afterwards cannot increase D any further, right? And therefore, this thing has to converge. So this network must converge after a while to some patterns. Now, when I say converge, you will find that, we will see later that if it converges to a particular pattern, then the inverse of the pattern, where I change every 1 to -1 and every -1 to 1, and the original pattern are functionally equivalent. So you can end up in a situation where it keeps flipping back and forth between those two. But if you consider both of these to be equivalent, eventually there is going to be a value, a configuration where it will converge. So now let me define, look at this guy D over here, right? This D was just the weighted sum of the products of pairs of neurons plus the biases weighted by the values. Let me define -half of that term as the energy of this network, of the Hopfield network. We'll see where this term energy comes from later. And so every time the Hopfield network changes its configuration, this energy, remember D increased, so minus D has got to decrease. So every time the Hopfield network changed its configuration to a different configuration, which means, it wasn't just a flip of the signs of everything, but an actually different configuration where at least one bit was fully different, right? Every time that happens, the energy must decrease. And so once again, you can think about it, this decrease, the smallest decrease in the energy is bounded. And so in a finite number of steps, the worst case, the energy can go to 0, right? So a Hopfield network is a loopy binary network with symmetric connections. Every neuron attempts to align itself with the sign of the weighted combination of the outputs of other neurons, the local field. Given an initial configuration, the neurons will begin to flip to align themselves with their local field. And this causes the fields at the other neurons to change. potentially making them flip, but that can change the field of the current neuron, making this flip all over again. And this evolution can continue, but each evolution of the network is guaranteed to decrease the energy of the network, and the energy is lower bounded, and the decrements are upper bounded, so the network is guaranteed to converge to a stable state in a finite number of steps. Everyone with me so far? If so, you have a poll. Pardon me? Yeah. This is just.
Question from Zoom.
Yeah.
So why can't delta D be 0 and the flips happen simultaneously for all each time?
Whether they happen simultaneously or not doesn't really change the factor, right? If they happen simultaneously, then delta D will be larger. Delta D will only be 0 when the two configurations are equivalent, meaning one is minus of the other.
I think they should be satisfied now, I guess.
Yeah. Okay, 5 seconds, guys. Okay, the first question, true or false? Second? Third? Who said true? Someone said true. Okay, why? Why? That was a smart answer, so you have to tell me why.
I'm not really sure, but I felt it's a shared parameter.
It's looping though. Can somebody tell me why that last one must be true? Someone on Zoom?
Uh,
Go ahead.
I think next, I'm sorry.
Go ahead, that's a good, continue.
I think the next layer is also the previous layer if it's taking form.
Exactly, right? So let's just consider a three neuron network. So this is like saying, so this is one evolution of the network, correct? And then this is that right? Have I got everything? No. This is the next evolution of the network. The weights over here are the same as the weights over here. That's why they are shared parameters. And I can unroll the evolution of the network, and it's like having one network which is infinitely deep, but we are saying that after a finite number of layers, the network is no longer going to change. Make sense? Right? So that was a smart answer even if you didn't know why. Okay. All right. But let's continue with the notion of a loopy network. So where did this energy concept suddenly jump out of? I defined an energy. Where did this jump out of? Comes out of physics. There's something called a spin glass. How many of you have heard of a spin glass? Someone on Zoom? Okay, this means that I'm safe. I can bullshit and nobody will know, right? So I'm going to continue. Now think of a ferroelectric material, ferromagnetic material, which has lots of these little molecules. Each of them is a dipole. They are magnetic. They always try to align themselves with the local field. Now the field at any particular, so if the field at any location is opposite to the orientation of that dipole, it's going to flip. But when the dipole flips, it changes the field at other places. And so those dipoles can flip simply because magnets try to align themselves with the local field. And so here's what you get. This is what physics seems to tell us from my understanding of it, that the field at the ith dipole is going to be a weighted sum of the magnetic fields, contributions of the magnetic fields of all the other dipoles in the medium, which is summation capital J, Ji, Xi. So it's the field at the jth position, or the ith position, right? So the contribution, this should have been Xj, right? Yeah. So This is the contribution of the jth dipole to the field at the ith position. And this is an external magnetic field. You may have some magnets outside the material. And if, so this is external, this is intrinsic. And if this field aligns itself with the dipole, then the dipole is not going to flip. But if the field is opposite, it's going to flip, right? And so the response of any dipole is going to be xi remains xi if the sign of the field is the same as the orientation of the current dipole, otherwise it flips, right? So a dipole flips if it's misaligned with the local field. How long will it continue? Now, what do we know about the energy of any physical system, the potential energy of any physical system? Or then any physical system is going to finally keep trying to lower its energy, right? This is a standard property of physical systems. They like to be, they're lazy. And so dipoles keep flipping. A flipped dipole changes the field at other dipoles. It will change the field at the current dipole, etc. When does it stop? We can define, okay, if I have a magnetic field at any point, and then I have a magnet, what is the potential energy of the magnet over there? It's the magnet's field, own magnetism times the field. You might remember this from your first year of college physics, right? So this is, and so we're going to define the Hamiltonian of the system, which is simply going to be minus of the value of the current dipole times the field, and J is the interaction between the two. So you sum this over all possible dipole pairs, plus of course, this is again minus the external magnetic field times the local dipole. So this is just, this is standard. If you remember anything about your physics, this is how they define energies, right? And this minus half outside is only it's a convenience thing so that you don't double count. And the system evolves to minimize this energy. This is the Hamiltonian of the system. It's like the potential energy of the system. It's going to evolve. That's why, you leave a ball up here. What does it do? It's going to come down because here the potential energy is high. It's going to try to go down to the lowest potential energy, right? And the rest becomes kinetic energy. So that's what the system tries to do. So it's going to try to keep evolving while to make the potential energy go down. How long will it evolve? So if you plot, now this is a really horrible plot because you're speaking of a discrete, binary patterns over here. So you can't plot binary patterns out in a line. Nonetheless, if I could say that if I define the configuration of all of the dipoles, each is either a +1 or a -1 as a state. And if I could lay the states out in a row, right? Then each state has a corresponding potential energy. And so you're going to have this potential energy contour. Now, if you initialize the system at any state with some potential energy, it's going to roll down, and you can think of the ball as the current state of the system. It's going to keep evolving. It's going to keep rolling down till it hits a local well. At the well, any further changes are going to increase the energy, so it's not going to move, right? And so the system eventually stops at one of the stable configurations, which is one of these local minima. And any jitter from the stable configuration returns it to the stable configuration. So if the system stops at the local well, if you kick it up a little, it's going to roll back down. In other words, at these stable configurations, the system remembers its current state. If you change it from there, it changes right back, right? You might have heard of shape memory alloys and things like that. What exactly are these? They're basically material which have a stable state. You crumple them and then you give them some energy by heating them. They're going to go back into the original state and recover their shape. That's basically this behavior once again, right? And so this behavior is very analogous to what we have at the Hopfield network, right? It's exactly the same thing. You have this field. The weight is like the coupling between dipoles, which also factors in the dielectric constant of the medium and other things. And then this B bias is like this external magnet that might be sitting somewhere and influencing the material. this system is going to have an energy just like the Hamiltonian of the spin glass, and it's going to evolve, and the energy will keep decreasing until it hits a local minimum. So again, this bias is like having an external magnet, right? But it's also like having an external unit that's pegged at 1. So in most of the analyses, we're going to assume that there is no external magnet, but it's not, you can also implicitly think of it as having one extra unit in the network that's always pegged at 1. So I'll just sort of switch back and forth between having that B and not having the B, but you have to keep this in mind. They're both strictly equivalent, okay? And so I can think of this term over here as analogous to the potential energy of a spin glass. The system will evolve until the energy hits a local minimum and stay there, right? So what does this mean? This network is going to evolve. These are all bits, right? Each of them is +1 or -1. If I set it at some configuration, the system is going to begin to evolve till an energy hits a local minimum. If I set the system at a local minimum, then what happens? Will it evolve? No, right? If I set it slightly off from a local minimum, will it evolve and go to the local minimum, right? So what kind of behavior is this? How many of you have heard of the term content addressable memory? Anyone heard of a CAN? So you partially raised your hand. The thing rings a bell. So what is a content addressable memory?
I just looked at the slide.
You looked at the slide before, so thank you. So what do you think it is? What do you think a content addressable memory is? So in a computer system, typically, how do you recover something that's in memory? How do you do it in a regular computer? Pardon me? Based on position, you have some location in the memory, right? And you say, okay, give me the value at -1, -1, 1, 1, -1, -1, or 0, 0, 1, 1. You give it the address, and you read the information from the address. So it's a position addressable memory, right? That's how we store it. But there's an alternate store mechanism for memory, which is content addressable, where that's how we sort of function. You vaguely remember some corrupted version of something, but when you start from there, you can recover the whole concept, right? The whole idea. So even in a computer, you can have this thing where if you remember a portion of a pattern, you can use that to recover the entire pattern. That's a content addressable memory. This guy is an instance of a content addressable memory. There are many ways of implementing CAMs. This is one, right? And so this is a content addressable memory. You can recall memory content from partial or corrupt values, also called associative memory. You remember something associated with a pattern, but that recovers the entire pattern. Now, when Hopfield originally discussed this, he was also thinking of human beings, the way we remember, right? You're going past some place, you smell something, and suddenly the entire event comes back to mind. You formed associations, right? That's basically the same kind of behavior that you have over here. So here's an example of a content addressable memory. This is from, I don't know what UQ, it's someplace in Australia. They had this nice picture on the web. So I downloaded it. The figures to the left are the original patterns that you're trying to store in a network. If you build a network to remember those patterns, and what do we mean by remembering those patterns? Those patterns are the patterns at which the energy is a local minimum, right? And then if you corrupt the pattern, like you could erase half the pattern, as in the lower case, or you can just add a whole lot of noise, as in the upper case, and let the system evolve, it's going to recover the entire pattern, right? There's still some noise. We'll discuss why the noise happens, but you get the idea. So this is a content addressable memory. Or here is a very nice video that someone made of, let me see if I can, where he actually designs the network. He's storing this pattern, the penguin and the clown, the penguin, and the globe. And then he's corrupted it. He lets it evolve. It evolves into this one. Corrupts it again, lets it evolve. recover the clown again. Right, and lets it evolve. It recovers the penguin. So you see how this works. This is a content addressable memory. Basically, you've built a device that stores these patterns. Then you give something that's corrupted, but if it's within the bowl for that pattern, it's going to recover the pattern. Right? So computationally, how would you do this? Very simple. I can initialize the network with some initial pattern. Then I can iterate through the rest of the neurons, through all the neurons. At each neuron, I'm going to check the field. If the output, the field has a different sign than the neuron, I'm going to just flip the neuron. I can do this one neuron at a time, or I can do this in bulk where I do this simultaneously for all the neurons. It doesn't matter. But then you keep doing this until the neurons no longer change, or to be more precise, until this energy converges. Okay, so I can write this in matrix format. If I write all of the weights between all of the neurons as a weights vector, a weights matrix, again, you can thinking about it in this term makes it much more obvious, right? So if I write it as a weight matrix, then the field at each neuron is simply going to be the weight times the current output of the neurons. You're applying an activation to it, which is a threshold activation that we just saw. And we keep just repeating this simple operation until now, when you write it in vector terms, the energy becomes minus 0.5 times y transpose wy, which is the matrix inner product between the outputs of the neurons, the activations and themselves. So a Hopfield net is a loopy binary network with symmetric connections. Given an initial configuration, the patterns of the neurons will evolve until the energy of the network arrives at a local minimum, and the evolution is going to be monotonic in the energy, right? The dynamics of the Hopfield network mimic those of a spin glass. Now, the network is symmetric. If a pattern y is a local minimum, then so is minus y. Why so? Can anybody tell me? Why? Look at this equation over here, right? If I replace y with minus y, does the energy change? Because it's y squared, correct? So anytime a pattern is remembered, if I flip the sign of every bit in the pattern, if I flip every bit, that is identical to the original pattern itself. So those cannot be distinguished, right? And the network acts as a content addressable memory. If you initialize the network with somewhat damaged version of a local minimum, it will evolve back into that pattern. So it effectively recalls the correct pattern from a damaged or incomplete version. Questions? Yes?
So practically speaking, you would have one network for every image that you try to store.
This was one network. How many images did he store?
They have different weights for each image, right?
Nope. So you're sort of, we'll get to that. Here's a poll first. Okay, this is an easy one, so 10 seconds. All right, does someone on Zoom want to tell me if that first statement is true? Anyone
True,
else think
it's true.
the second,
True,
third,
true.
the third, not really. Okay, and it turns out to be a very complicated problem, but the first two are true. And that's because this is an integer programming problem. I have a quadratic objective function, but the solutions states are all on the corners of a hypercube. So if this were real, then you could just analyze the weights matrix and say where the minimum lay. But because now this is, a Boolean problem, it's actually a very complicated solution, complicated problem. Even though it's quadratic, it's not convex. Anyway, so to address the other questions that you guys came up with. First, obviously, you don't want a separate network for every pattern you store. What is the point of this? If you have a separate network for every pattern you store, you might as well just have the pattern. It's no memory at all, right? What you want is a single machine which can store many different memories. It's not like I have a separate head for every event that occurred in my life. And so I'm walking around with millions of heads because, so many things happen in my life all the time. I'm storing all of these, but I'm storing them in one head. You want the same kind of behavior out here. So how do we make the network store a specific pattern or a set of patterns? How many patterns can we store? And how do I retrieve a specific pattern better, right? So these are all questions. And I'm going to sort of give you the original answers as described by Hopfield today, but we'll do a more analytical and we'll look at a more analytical approach in the next class, which makes the whole thing somewhat prettier. And we'll show how this actually is a generative model. Now, the reason we are talking about Hopfield networks this late into the course is that we wanted to introduce the notion of generative models, which we've already done with VAEs and GANs. This is another, right? So how do we teach a network to remember this Chip and Dale image? Now, clearly, if the image has n pixels in it, you need one neuron for every pixel. So you're going to need a network with n neurons, right? Each neuron is going to store, remember, one pixel. Every neuron connects to every other neuron. So so how many weights will we have? It's going to be order n squared. It's going to n times n minus 1 over 2 if it's symmetric. Otherwise, it's going to be n squared minus n if it's not symmetric, right? We will continue assuming symmetric. So now, again, our network which stores a pattern P also naturally stores minus P, because E of minus P is the same as E of P. We want to remember this, right? Now, a network can store multiple patterns because you can have multiple local minima in your in the energy surface. Every stable point in this potential energy surface is going to be a stored pattern. So you can design the net to store multiple patterns. Again, remember that every time I'm storing a P, I'm also storing a minus P. Actually, it's a little more complex than that. If I have the bias term, then I have this one guy fixed in the corner whose value is always 1. Nonetheless, you still have the same behavior. Every pattern actually represents 2 patterns, okay? So we want to design the weights over here such that this energy is a local minimum at the desired pattern. That's how you make it something that's recalled, right? And how do we do that? So the first guess, let's look at the behavior. There are 2 different behaviors we want. One is stationarity, the other is stability. What do you think I mean by stationarity? Anyone? What do I mean by stationarity? What do you think I mean?
There's a stable state somewhere where it gets to.
So I want a pattern to be stationary. So what does that mean?
You don't keep changing the pattern while it is getting too low in that pattern.
So if I'm trying to remember a specific pattern, I want it to be stationary, meaning if I set the network at that pattern, it shouldn't evolve. Correct? I want it to be stable. What does it mean? If I perturb it a little bit from that pattern, it should go back to that pattern, right? There are 2 characteristics. Stationarity is not the same as stability. We'll see why. So I want a pattern to be stationary, which means that I want the sign of the field at every neuron to be the same as the sign of the neuron itself, right? If this happens, we are guaranteed that the network is not, that neuron is not going to flip. This must hold for every single neuron. So let's try a very simple thing. Say I'm trying to store only one pattern. I'm going to try Hebbian learning. How many of you remember what Hebbian learning? What was Hebbian learning? Yeah.
There was the we keep updating it with the constant value, so there is explosive.
Yeah, but what was Hebbian learning? There's more than that, right? How did we update it? What was the update? It was the product of the input and the output, correct? So the Hebbian rule over here says that the weight, if I start off at 0, I'm going to make the weight equal to the product of the input and the output. In this case, Wij is going to be Yi times Yj, right? So let's use this very simple Hebbian rule to set the weights. Then let's see what happens. I'm going to say Wji equals Yj Yi. So then the sign of the field at, say, the ith neuron is going to be Wji times Yj summed over all j not equal to I, correct? But Wji is simply going to be Yj Yi for the stored pattern. So in other words, I have Yj times Yj. The y's are all either +1 or -1, right? So this is basically Yj squared times Yi. Yj squared is always going to be 1. So in other words, this guy is going to be this whole thing. This Yi comes out, the rest is just some positive term. So you're guaranteed that the sign of the field at each neuron is exactly the same as the value of the neuron itself. The sign of the neuron itself, right? So this is stationary. Everyone see how this is stationary? Right, guaranteed stationary. Now what about stability, right? Now let's look at the energy when I consider the Hebbian rule. So I can say so the energy is the sum over all pairs of neurons, or the weight times the neuron values. Now at the pattern that I'm trying to remember, Wji equals Yj Yi, right? So in other words, this is simply going to be Yj Yi, Yj Yi, so it's Yi squared, Yj squared, which is just 1. This is basically the lowest the energy can possibly be, so long as my weights are binary, right? So if this is the lowest the weights can possibly be, this means that at the pattern I'm trying to store, I have an energy where the energy cannot be any lower. Does that mean the energy is stable? The pattern is stable? It's a local minimum, guaranteed, right? Eric,
Can't weights be flows?
so the way we've defined the weight is Yj Yi, right? Is a Hebbian rule. So for those weights, given those weights, the stationary pad, this is the lowest energy it can be, right? All the weights are +1 or -1.
So we were saying if you make the weights +1 or -1, then it.
I'm saying that if I make the weight equal to the product of the two terms, then for the pattern I'm trying to remember, then when I set the network at that pattern, the energy is the lowest it can be. There's no arrangement of the Yj's and Yi's for that particular setting of weights, which has a lower energy.
Couldn't you make the weights like 0.1 Yj and 0.1 Yi?
So I'm saying, given the weights, this is how I've set the weights. Once you choose the weights, is there any setting of the Y's which can give you a lower energy? Right, so I've designed the network, and once you've designed the network, the weights are fixed. We want to show that this specific pattern has the lowest energy. So the W's are given, right? So for the given W's, this is the energy. You can't go lower than that. So this is also stable, right? The pattern is stable. And so it turns out that if I simply use the simple Hebbian learning rule, where every weight is simply the product of the 2 bits on either side, this is a very stationary and very stable pattern. But then let's look at it, right? I'm looking at a 4-bit network, and I know that 4 bits can be represented in a 2 cross 2 Carnot map. We've seen this. We've seen Carnot maps way back in the second class, where in a Carnot map, every square is adjacent to every other square, right? This is a topological representation, which is valid, and I can actually plot energy contours on this. So I'm trying to store this pattern, which is 1 minus 1, 1, 1. When I try to store it, and if I design the weights using the Hebbian learning rule, this is the energy plot that you've got. And if you look at this energy plot, the lighter the color, the lower the energy, right? You can see that this guy has the lower energy, as does its negation. But if you start at any point, the network will evolve towards lighter colors all the time. That's because it's going towards lower energies, right? So regardless of where you begin, so if I began over here, it's going to go maybe here or here. If it goes here, then it next goes here. If it goes here, it evolves and goes here. Both of these are equivalent patterns. So the yellows are local minima, and no matter where you start from, the network is going to evolve through to the pattern that you're trying to remember. So this works, right? At least in the 2 cross 2 case. But then, suppose I want to store more than one pattern. Then here's what I can do. I can continue to try to use the Hebbian learning rule because I know it works for one pattern, right? So I'll still use the same Hebbian rule, except that I'm going to compute the average of this product over all the patterns I'm trying to store. If I do this, what happens? Will this remember all the patterns I want to remember? And Hopfield showed that if I do this, if I use the Hebbian learning rule to compute my weights, then for a network with n neurons, you can store up to 0.15 n patterns with a probability of success or probability of failure less than 0.004. So what does this mean? That 96% of the time, the pattern that you're trying to store will actually be stored as a local minimum. Now, where does this math come from? It's very simple, right? So the Hebbian learning rule gave us this for the weight, right? So for any pattern to be stable, you want the field times the bit. The product of the field times the bit to be greater than 0 for all of the bits. And so if you sum this over, and this Wij is simply the average of the products of the bits over all the patterns that you're trying to store. Now this guy here, so over here all I've done is I've taken this Wji, plugged in this value, and so I end up with this equation over here. But then, so Yip is the specific pattern that I'm trying to analyze. Is this pattern really stable or not? Is it being remembered? So the superscript P is the specific pattern I'm trying to analyze. And so that's why this term comes from the pattern I'm trying to analyze. The inner term comes from the computation of the weights. Now within the weights itself, I can separate out the pattern P and all the rest of the patterns. And so if I do that, I can rewrite the weights as the contribution of this target pattern that I'm analyzing and the contribution of all of these other guys, the remaining patterns I'm trying to store, right? And for this term, I know that it's yi squared, yj squared. So this first term is always going to be 1. It's a product of a pair of 1s averaged over all the patterns. And so it's going to be 1. And this second term, we don't really know what it is, right? So for a pattern to be stable, you want to make sure that this guy is greater than -1. If it's less than -1, that pattern is not stable. It's going to flip. Some bits are going to flip. So the second term is what they call the crosstalk term. And the crosstalk term must be greater than -1 for every single bit, for every single, for any pattern. And if it's less than -1, then that pattern is not stable. So once you write things this way, then you can actually compute. If you just assume that you're going to be choosing the patterns to store at random, uncorrelated patterns, then you can compute the probability that this crosstalk term will actually become less than -1. No need to actually go into the math, but then we can sort of, for a large enough binomial variable, we know that the probability distribution approaches Gaussian. So for patterns with very many bits, you can show that the number of patterns that you can store where you can guarantee that the probability of this crosstalk term being less than -1 is less than 0.004 is about 0.14n. So if I have an n-bit pattern, then I can store up to 0.14n patterns using the Hebbian learning rule with the assurance that there's less than a 0.4% chance that the pattern isn't actually remembered, right? But this only holds if all the patterns are randomly chosen. They're uncorrelated. So Hopfield's analysis showed that a network of n neurons trained by Hebbian learning can store up to 0.14n random patterns with a low probability of error. Now, but these patterns, you want them to be as far apart as possible, right? What is the farthest apart that you can have that two binary patterns can be? Pardon me?
Opposite?
Opposite, they're the same pattern, right? You want them to be orthogonal. So in other words, if I take the product of the two patterns bit by bit and sum them up, then this must be 0, which means the two patterns must match in as many bits as they mismatch. If I have 4 bits, then the two patterns can match in 2 bits, but they must mismatch in 2 bits, and the two bit patterns are orthogonal. And so that's the best case. If I randomly choose patterns, there's no guarantee that the patterns are going to be orthogonal, right? But anyway, so what does this actually mean? Let's go back, and I'm going to go back and look at this Hebbian learning, this Cardo map to show the energy contour for Hebbian learning. The figure to the left shows the pattern I'm trying to remember. The figure to the right shows the energy contour, and we see that if I'm trying to store only one pattern, that pattern is actually a local minimum. It will work. This network will actually recall that pattern regardless of where you started from. But now, let me try to store these two patterns. These two patterns are orthogonal. What do I mean by that? This guy is 1, 1, -1, -1. This guy is 1, 1, 1, 1. So you can see that the number of bits that they match equals the number of bits that they mismatch, at. And when I do that, and I use the Hebbian learning rule that we just saw, the energy contour is shown to the right. Okay. Now, what we see is that these patterns that we're trying to store are actually stationary. They are yellow. They are the lowest possible energy. If you start the energy network in that pattern, it's not going to change. But if I flip one bit, then something odd can happen, right? If I flip one bit, it could move here, and the next evolution can actually take it to the next pattern. So they're not really stable. They're stationary, but they're not stable, right? And now suppose I choose two non-orthogonal patterns. If I choose two non-orthogonal patterns, which means that they differ in fewer than 2 bits, here you'd expect that because the difference is smaller, they'd be more confusable, but then you get some strange behavior. That's not what happens. If I use the Hebbian learning rule, I find that not only are they both stationary, they're also stable. If I flip a bit, there's a pretty good chance that I'm going to recall that pattern, right? Now, 2 is much greater than 0.14n, right? So clearly, Hopfield's assumption that you can store up to 0.14n patterns, we are sort of violating that. It's a probabilistic statement, so you aren't violating anything, but we're actually getting to store. I chose these things randomly, and you see that you're actually getting to store more than 0.14n patterns over here, right? What if I try to store 3 patterns in a 4-bit network? Once again, we find here that all 3 patterns that I'm trying to store are stationary. Now, these are 3 orthogonal patterns. If I take any 2 patterns, they differ in 2 bits. but you can't really recall them. None of them are stable. If I flip a bit, you have no idea where it's going to go, right? And on the other hand, if I chose 3 patterns which are not orthogonal, so the difference is smaller than 2 bits on average between any 2 patterns, I actually find that firstly, not all of the patterns are storable, not all of them are stable, stationary, and some of them are stable and others are not. So it's kind of confusing behavior. It's not really clear what's happening when I use the Hebbian learning group. I can try to actually do something even better. I can try to store 4 orthogonal patterns. And I find that 4 orthogonal patterns are able to give me, if I use the Hebbian learning rule, all 4 are stationary. But then something strange happened over here. Every single pattern is stationary, right? It doesn't matter how I initialize the network, it's not going to evolve. Can anybody tell me why this is happening? How many axes? This is a 4-bit network, right? How many dimensions will I need to represent it? 4. So how many axes can I have? 4 orthogonal axes, right? And any pattern, so you can think of this as creating a weight matrix where all 4 of my patterns are eigenvectors of my weight matrix. And so any combination of the eigenvectors is also going to be stable. We'll see that in a bit, okay? So this, and if I have 4 non-orthogonal patterns, you end up with 1 stable pattern, but then something interesting. For every stable pattern, you get some ghost patterns that you don't really want to store. But they're also stable in that although they are not necessarily the least possible energy, all the neighbors actually have higher energy than the pattern itself, right? So for a network of n neurons, you can store up to 0.14 n random patterns, the fuzzy statement. What does it mean to say stores 0.14 n random patterns? Does it mean stationary? Does it mean stable? It's not really clear, right? And what if the patterns we want to store are not random? We saw that if I explicitly make my patterns non-orthogonal, they're more likely to be stored than if they're orthogonal, right? So n equals 4 is kind of a small thing. You can't 0.14 n is less than 1. So maybe we want to look at something bigger, like n equals 6, because 0.14 n is at least 1, right, over here. So here for n, a single pattern is both perfectly stationary and stable. You'll find that it's a bowl, right? But then there are many spurious minima. Spurious minima are minima where the energy in that configuration is lower than the energy of all of the neighbors. And when the energy is lower than all of the neighbors, if you start it somewhere in that neighborhood, it's going to go to that energy. These are what we would call fake memories. As human beings, we suffer them too, right? You remember things that never happened. And who was it? Was it Mark Twain who said, I pity the man who can only remember things that happened. But anyways, so Hopfield networks are good at this. Now, if I try to store 2 patterns, then they're both perfectly stationary and stable. But once again, we find that there are many spurious memories, things which are recalled if you're close enough, although the target patterns you're trying to remember are indeed recalled. Now, again, when I'm trying to draw a 6-bit Carnot map, you have to really remember that these are many 4-bit Carnot maps stacked on top of one another, so it's not easy to visualize what's going on. So we can just keep drawing these patterns, right? And in general, what we find is that there are many situations where you can store more than 0.14 n patterns. But then in all cases, except when you're trying to store only 1 pattern, you have this, and even when you're trying to store only 1 pattern, you have the situation where you can have spurious memories. Local minima, which are not what you're trying to remember, which will nevertheless be, will be an attractor, because if you start next to it, you're going to end up in the local minimum, right? So these are what I'm calling parasitic patterns, undesired patterns that also become stable or attractors. Now we are seeing there's apparently a capacity to store more than 0.14 n patterns, and 2, we have these additional states which are memories that are not meant to be recalled but end up being recalled, okay? So what exactly are these bogus parasitic memories? If you plot your energy contour, you might find that, for instance, you're trying to design your network to store these patterns, but then you're going to end up with these little dips between the patterns. And these little dips are also local minima, which are your spurious energy, spurious memories. And more generally, if I'm trying to store, say, patterns YA, YB, and YC, then the sign of the sum of these patterns also ends up being a memory. And so this is why you end up with spurious memories, because these are things which are averages of the patterns that you're trying to store. So we can think of it this way. If I have two patterns which are here and here, every pattern that's on the line between the two, which is an actual binary pattern, is also going to be remembered, right? So it seems, so we can speak of the capacity of a Hopfield networks. It seems possible to store more than 0.14n patterns. That is, it means it might be possible to obtain a weights matrix such that if I have n neurons in the network, I can remember more than 0.14n patterns. Patterns that are non-orthogonal, which differ in fewer than half the number of bits, are strangely enough more memorable than patterns which are far apart, which is somewhat counterintuitive. Now, all of this is based on using Hebbian learning for trying to design the network. Can we design a network without using the Hebbian learning rule, which will actually do a better job? So here's what we've had. The story so far: a Hopfield network is a loopy binary network with symmetric connections. Given an initial configuration, the pattern of neurons will evolve until the energy of the network hits a local minimum. The network can be designed to store designated memories. And for something to be called a memory, it must be both stationary and stable, meaning if you initialize the network in that pattern, it mustn't change. If you flip a bit or two, it should go back to it. And you can train it using Hebbian learning, but it doesn't really seem to work, right? Hebbian learning allows you to store a small number of patterns, one or two, but then when you try to store more than that, in many situations, you get very bizarre behavior. Nonetheless, even with Hebbian learning, it seems that we might actually be able to store more than 0.14n patterns for an n-bit network, right? So there's a poll. Okay, 5 seconds. All right. Sanjana, is the first statement true? The second and the third? Right? All patterns won't necessarily be remembered, right? And an n-bit Hopfield network may actually remember more than 0.4 and 14n patterns. It may remember lesser. That number 0.14n is basically based on the assumption of randomly chosen patterns with some very specific assumptions, okay? So I'm going to claim that using an n-bit network, I can always store up to n orthogonal patterns, right? So that they're stationary. I'm not speaking of stability. I'm speaking of stationarity, right? And secondly, I'm going to claim that I can, we have this problem over here, which is this guy, that you have these spurious memories. And so if I start something over here, I probably want to remember this, but because of the spurious memory, I get dragged into the wrong memory. And so I'm going to claim that we can avoid those by adding a little bit of noise during recall, right? So, but let's analyze the first question first, right? Now, when I'm thinking of Hebbian learning, the Hebbian learning rule was that the weight between the jth and ith neurons was simply yj, yi. The neuron doesn't have any weight with itself. So if I want to write out the weights matrix, if I write the entire pattern as a vector, the pattern that I'm trying to store as a column vector, then the weights matrix for a single pattern is y times y transpose minus I, because you want all the diagonal elements of the weight matrix to be 0. Specifically, we are saying over here that none of the neurons actually has a connection to itself, right? This was the structure of the network, the way we defined it. There's no connection from the output of a neuron into itself, its own input. And so I can write this weight matrix for a single pattern as y transpose minus I. If I'm trying to store np patterns, then it's going to be the average of this guy over all of the patterns. If I write all of the patterns into a single matrix, so every pattern is a column vector, I can stack them up into a row, into a matrix, all of the patterns, right? So if I'm trying to store some 3-bit patterns, and if I have 10 of those, I can stack them into a 3 cross 10 matrix, which I'm representing as capital Y. And so I can write this weight matrix as 1 over n times y transpose minus the identity matrix, subtracting the identity matrix to make sure that the diagonal entries of the weight matrix are all 0, right? And so if I want to analyze the behavior of the network, I just have to analyze this guy. Now, as it turns out, this matrix is symmetric. It's symmetric because it's y times y transpose. It's also positive semi-definite. And we can see why it's positive semi-definite. Observe that if I write my weight matrix using this rule, which is my Hebbian learning rule, the behavior of the network using this weight matrix is the same as the behavior of the network using y transpose as the weight matrix. And the reason for that is that if I consider the energy for any pattern, it's y transpose times this guy, the weight matrix times y, which is just expanding out the weight matrix, 1 over np times y transpose lowercase y minus n, simply because y transpose times I times y is just the inner product of the pattern with itself, right? And the pattern has n bits. So the second term is n. So the energy when I use this is the same as, basically if I use just this guy as my weight matrix, then in one case I'm going to have, there was a chalk. In one case I'm going to have y transpose, this is capital Y transpose y. In the other case I'm going to have 1 over n times y transpose y transpose y minus n. If you look at these two, the only difference between these two is if this is a bowl as a function of y, this is going to be a shallower bowl shifted by n, right? But both of them are going to have the same shape. The only difference is the additional height and the scaling, right? So because this one hasn't, or shifted down by n because of the additional minus n. So I can analyze this guy and find out the location of the minimum. And that should tell me the same as the location of the minimum for this guy. So it's easier for me to analyze by this matrix. And this, like the original weight matrix, is also positive semi-definite, right? So I'm just going back. Here is the energy of the network. If you want to analyze the behavior of the network, you have to look at the energy of the network, right? Now, this is a quadratic. And for Hebbian learning, the weight matrix is positive semi-definite, right? When you speak of a positive semi-definite, is this, what kind of a bowl is this going to be? Does this bowl have a minimum or a maximum? it's like, think of it, put it in scalar terms. It's like saying minus y times, if I say positive semi-definite, in a scalar term, it's like having a positive value, right? So it's some minus ay squared, correct? Is minus ay squared this kind of bowl or this kind of bowl? It's going to be this kind of bowl, correct? So if that's, so the bowl is going to look like this, correct? Furthermore, so if I'm ignoring the bias term, if I take a cross section at different heights, the level curves are going to look like these ellipses, concentric ellipses. Now, also, the patterns that you're trying to remember, the patterns that the states that the network can take are all going to be either +1 or -1 at each of the bits. So they're going to be the corners of a cube where any coordinate takes the value 1 or -1. So in 2 dimensions, it's going to be one of the 4 corners in yellow. In 3 dimensions, it's going to be a 3-dimensional cube where every corner is going to be, where every coordinate is either 1 or -1 for each corner, right? And now look at this guy here. Those 4 yellow dots represent the only configurations that the network can take, right? And now furthermore, if you look at the inner circles, based on this pattern over here, the inner circles are further up, right? The inner ellipses. So these have higher energy contours than the outer ellipses. So of these 4 configurations, which are the stable configurations over here? Can you tell me which ones? The first and the third, right? So these guys are going to be your stored patterns because they're further away from the center, ellipses that are further out. And so regardless of, they're in fact the 2 mirror images in this particular example because I have only 2 bits. And regardless of where you start, it's going to end up at one of those 2 places, right? Because that's where the minima are. Or more generally, if I'm looking at a 3-bit pattern, then all the valid patterns are going to be the corners of this hypercube, 3-dimensional cube. And if you plotted the energy contour, you're going to find that some corners have lower energies than other corners, and those are going to be the stored patterns. But then you're also going to find, in this case, you may not see it, but you might find that for some corners, the neighbors are higher than that pattern itself, even though that pattern is not something you're trying to store. So those would be ghosts. Now, ideally, you want these based on this kind of a figure. You would assume that if you want a pattern to be remembered, the patterns that you want to remember must be as far apart as possible, right? So that if you flip a bit, for it to end up in the wrong corner, it must travel a longer distance. But that's not actually what ends up happening. Now, to see how the network evolves, this is the evolution of the network, right? Y equals sine of W times Y, right? Now, if I give you a vector and I multiply it by a matrix W, 2 things happen. The vector is going to rotate and it's going to elongate. Now, so if I start off with some vector, Y times W times Y is going to go to this new vector. But then when I take a sine, it gets snapped to the nearest corner, right? And a pattern is stable if W times Y ends up in the same orthent. It doesn't go into a different orthent, because if it went into a different orthent, it's going to snap onto that corner, right? So a pattern is stationary if it stays onto the same orthent. Now, so we want a pattern for any stored pattern, sine of WYP equals YP, right? So for training, I want to design my W such that this holds. And when is sine of WYP equal to YP? Guaranteed. When YP is an eigenvector of W, right? W is a symmetric positive semi-definite matrix. So all of its eigenvalues are positive, correct? So which means W times Y equals Y, or W times Y equals has the same sign of Y if Y is an eigenvector of W. So if I have a collection of vectors and I want to design a W such that all of those patterns are kind of stationary, I want to make sure that each of these Y's is an eigenvector of W. And because W is symmetric, the eigenvectors have to be orthogonal to one another. So this is only guaranteeable if all of the patterns you're trying to store are orthogonal. More generally, you just want the orthent of Wy to be the same as Y for the patterns that you store, so that it doesn't go into a different orthent and doesn't get snapped into a different corner, right? So why only n patterns, right? Symmetric matrices have orthogonal eigenvectors. You can have a max of n orthogonal eigenvectors in an n-dimensional space. So Wy can have at most n eigenvectors, which means the network can store at most n patterns, right? On purpose. So what is the largest number of patterns that can be stored? It's going to be n. Now let's assume that I have some k orthogonal patterns I'm trying to store. Which I store into this matrix Y. If I design my W matrix as Y times lambda times Y transpose, if all the Y's are orthogonal, this is like, an eigen decomposition of my weight matrix. If all the eigenvalues are 1, this gives me my Hebbian learning rule. Exactly the Hebbian learning rule, right? And so once I use this, then just by simply analyzing the fact that these are eigenvectors of this matrix, weight matrix, you can guarantee that all of these patterns are stationary, right? But suppose I have fewer patterns than n. Then it's like saying I'm going to choose a bunch of other patterns which are stationary to the one, which are orthogonal to the ones I have. And so I'm going to create this larger W matrix where these are the fake patterns that I'm not trying to remember. I can create my weight matrix, but then I can set the eigenvalues to be 0 for these guys. That's basically what it looks like, right? And so now, what does this mean? If I have n orthogonal patterns, then the eigenvectors span the space, right? And here is something strange. If my eigenvectors span the space, if I'm storing n orthogonal patterns, now if I have n orthogonal vectors, any vector can be represented as a linear combination of these n orthogonal vectors, right? So I can say, so if y1 through yn are my patterns I'm trying to store, they're orthogonal. I've built my weights matrix so that these are the eigenvectors of the weights matrix. Then if all the eigenvalues are 1, w times y, where y is some linear combination of the patterns I'm trying to store, is going to be a linear combination of a times wi, right? Where w times yi is simply going to be yi because it's an eigenvector. So what this means is that regardless of the vector I start off with, after one evolution, I'm going to end up with the same vector itself. So what this means is that every single pattern, if all the patterns I'm trying to store are orthogonal, and I make my weight matrix such that these vectors are its eigenvectors, and the eigenvalues are 1, I'm getting a network where the patterns I'm trying to remember are indeed stationary, but it's a useless network. It remembers everything. It's basically noise. So, and the same thing, if I am trying to store fewer than n orthogonal patterns, I have these guys whose eigenvalues are 0. So anytime I start off evolving from some random pattern, it's going to eventually end up as some linear combination of the patterns that I'm actually trying to store. And every linear combination of these patterns is stationary. So the simple Hebbian learning rule doesn't really work because the Hebbian learning rule assumes that all of the eigenvalues are 1, which is not a great idea. This essentially ensures that any linear combination of the patterns you're trying to store, if it is also a binary pattern, it's also stationary. And you get lots and lots of spurious memories, right? So anyway, what happens when the patterns are not orthogonal? Or when I'm trying to build my matrix instead of just averaging all of the patterns and outer product of the patterns I'm trying to store, I present some of them more than once. If I present some of them more than once, it's like saying their eigenvalues are greater than 1, right? So in this case, how would an evolution of this kind go? Where is this? Oh gosh, how would this evolve? It's really hard to say if the patterns are not orthogonal. But in general, it's not going to be a very nice behavior, right? So the bottom line is that with a network of n units, the maximum number of stationary patterns is not the maximum number of patterns you can try to store is n, but the maximum number of stationary patterns is exponential in n. Why? Because we saw that if the patterns are all orthogonal, then every combination of these patterns is also stationary. And so even though you're trying to store n patterns, you can end up storing 2 raised to n patterns. And this is not a network you want. It remembers anything. It's a very convenient network. It will remember anything you want it to remember. So that's not what we want. So, but there is a theorem which says that if you want to have a specific set of k patterns, so long k is less than or equal to n, I can always design a network such that these k patterns are local minimum. And how can I design this? This may come at the cost of some parasitic memories, but it's always possible to design such a network. And how do we find this network? And what can we do about these parasitic memories? So this is going to be the topic of the next class. In theory, the number of stationary states in a Hopfield network can be exponential in n, but the number of intentionally stored patterns can be as large as n. Doing something naive like the Hebbian learning rule is not going to cut it. So what else can we do? We'll look at this in the next class. Any questions? Yes?
I'm a little bit curious about how the number 0.14.
That's over here. Right. So if you just use the Hebbian learning rule, then we had this proof, right? That for any pattern to be stable, this guy has to be greater than 0, correct? But in the weights, we chose this as the weight. I can choose the contribution of the target pattern and pull it out. And this is the contribution of the remaining patterns. So if I want to see if a pattern P is stable, then I have to evaluate this guy, correct? And this term is always equal to 1 using the Hebbian learning rule. So we want to make sure that this term is greater than -1 so that the sign of the whole thing stays positive. And you can compute the probability that that term is actually greater than -1. It turns out to be 0.14 for k, if the number of patterns you want to store is 0.14n, then that probability is 0.004, 0.996.
We can't find the exact calculation.
This is actually, it's actually on the slides. You can check it out. This is the actual arithmetic, exactly. But it's also in Hopfield's paper. Thank you.